What do you think happens when the world's mightiest locomotives are monumental mistakes? Built with audacity, money, and impossible promises, these giants roared into service only to stall, crumble, or explode their reputations. These machines had massive budgets, record-breaking specs, and impossible promises. And yet, when it mattered most, they simply didn't work. So how did railroad giants become legendary failures? Let's count down the greatest failed locomotives in history. Number 10. Fowler's Ghost. Starting off our list with Fowler's Ghost, the doomed attempt to hide steam. This is the archetypal Victorian experiment gone sideways. Sir John Fowler designed a locomotive to run in covered tunnels without belching smoke or steam, a real public safety design challenge for London's brand new Metropolitan Railway. The idea was simple in theory. Instead of a normal working fire, pack the boiler with fire bricks and recondense exhaust steam, so tunnels wouldn't fill with choking fumes. It was elegant on paper and terrifying in practice. What happened when they tried to make a steam engine stop sounding like a steam engine? On its first trials, the condensing leaked, the boiler ran dry, the feed pumps jammed, and the engine nearly exploded. The design couldn't keep pressure reliably, and rather than a quiet miracle, the locomotive was a dangerous embarrassment. It was sold off and quietly scrapped decades later. What really hurt Fowler's Ghost wasn't just the leaks or the jams. It was the fact that crews didn't trust it. When an engine feels unpredictable, people stop wanting to work near it. A single miscalculation in heat, water flow, or pressure could have turned a bold public safety idea into a catastrophic tunnel accident. It proved early on that hiding steam wasn't just an engineering puzzle, it was a life or death risk. That fear alone was enough to doom the project. Even if the engine had improved later, confidence was already gone. If you thought no smoke was ambitious, wait till you meet the engineers who tried to make a steam engine with 14 driving wheels. Number 9. Soviet AA20. Soviet AA20, the 7-axle monster that wrecked the track. The AA20 is one of those headline makers, a single gargantuan Soviet prototype with 14 coupled driving wheels, that's 7 axles of drivers in a rigid frame. It was absolutely huge, with enormous axle loads and a tractive effort designed for brute force hauling. The theory was simple: more wheels, more power. The reality was a rigid, unforgiving wheelbase that hated curves and punished the track. Only one was ever built. Could raw size and power alone make an engine unusable? Yes, the AA20's rigid 7-axle wheelbase generated massive track forces. It could pull like a beast, but it damaged rails and derailed on ordinary curves, so it never became a fleet. The lesson here wasn't subtle. Railways are systems, not test benches. An engine doesn't exist in isolation. It must live within curves, switches, bridges, maintenance depots, and timetables. Honestly, the AA20 didn't fail because it was weak. It failed because it was too strong for the environment it was meant to serve. What's unsettling is that this wasn't an isolated mistake. Over and over again, railways would repeat the same pattern, chasing raw performance without asking whether the rest of the system could survive it. And some of the most famous failures on this list fall into that exact trap, just in very different ways. If the AA20 showed what happens when raw power beats up the track, the next one showed what happens when that power turns inward on the engine itself. Number 8. Erie Triplex. From a wheelbase the size of a small building, we move to an American experiment that piled driving wheels everywhere, the triplex. Erie Triplex, the everything but the kitchen sink steam. The Erie triplexes were literal experiments in more is more. 3 sets of driving wheels, compound cylinders, and claims that they could move unbelievable tonnage. Some accounts even boasted they could shove hundreds of freight cars as a helper. But reality hit hard. The rear engine rode on the tender and lost adhesion as coal and water were burned off. They were slow, complex, and best used only as downhill pushers. All were scrapped within a couple of decades. If you give a locomotive more driving wheels, will it always pull more? Not if those wheels lose adhesion. As fuel and water were consumed, the triplex's tender-driven unit went from grip to slip, so its massive theoretical power rarely became reliable pulling in real service. The triplex wasn't just a mechanical oddity, it was a lesson in diminishing returns. More cylinders, more frames, more axles didn't mean more productivity. Sometimes complexity itself becomes the enemy of performance. Now, instead of adding wheels, British engineers tried something completely different, a radical boiler design. Number 7. LNERW1. Meet the LNERW1, the high-pressure oddball. Nigel Gresley's W1 packed a marine-style water tube boiler into a railway locomotive to chase extreme steam pressure and efficiency. It worked in flashes. The engine impressed on headline runs, but the exotic boiler was maintenance-heavy, temperamental, and far too complex for everyday rail service. Eventually, it was rebuilt into something more conventional, but the original experiment remains a fascinating near miss. What made W1 so compelling is that it wasn't a failure of imagination. It was a failure of practicality. Railways need repeatability. They need designs that can be repaired at ordinary depots by ordinary crews. The W1 demanded specialists, rare parts, and constant attention. It wasn't wrong. It was simply too early. Number 6. PRR S1 Duplex. Now moving on with our list, we have the PRR S1 Duplex, a streamlined statue that didn't fit the rails. The Pennsylvania Railroad's S1 looked like something from an Art Deco dream. Impossibly long, brutally heavy, and designed for astonishing speeds on paper. It used a duplex drive with enormous wheels and cutting-edge engineering. But grandeur came at a cost. It was too long for many turntables and yards, struggled on tighter curves, and existed as a single, expensive experiment. A marvel to see and a nightmare to operate. Could a locomotive be so big and beautiful that it becomes unusable in the real railroad world? Absolutely. The S1's sheer size clashed with existing infrastructure, making it spectacular on display but painfully limited in everyday service. The tragedy of the S1 is that it wasn't badly engineered, it was over-engineered for a system that never evolved to match it. From lavish steam giants, we jumped to electrics that promised speed and delivered frustration. Number 5. GEE60. GEE60, an electric that undercut Amtrak's needs. On paper, the GEE60 looked perfect. Huge horsepower, serious tractive effort, and a modern electric design meant for passenger trains. Amtrak bought them expecting high-speed performance. But the E60 was geared and sprung more like a freight locomotive. At the speeds passengers demanded, it rode rough, suffered reliability issues, and developed a reputation for being uncomfortable and troublesome. Power alone wasn't enough. If an engine has massive horsepower, why can't it be a great high-speed passenger locomotive? Because speed needs more than power. Suspension, gearing, dynamics, and electrical systems matter just as much. The E60 had muscle, but not the finesse required for smooth, sustained high-speed passenger service. It revealed a critical truth of rail design. The mission defines the machine. You can't simply repurpose brute strength for elegance. The E60 had plenty of muscle, but it was built with a freight mindset. And at passenger speeds, that showed. The ride felt rough, components were under stress, small problems became big problems. To passengers, it didn't feel modern or comfortable. To crews, it felt like the locomotive was always working against its own design. Not every failure is dramatic. Sometimes it's simply bad timing and bad engineering choices like the SD50. Number 4. EMD-SD50. EMD-SD50, the rushed upgrade with reliability bills. The SD50 was supposed to be a power bump, squeezing more horsepower from a proven diesel platform. On paper, it looked like the perfect bridge between old and new. In reality, higher stresses on components, electronic issues, and mechanical wear created costly maintenance headaches. Many units were later rebuilt or detuned. The lesson was brutal. Pushing an older design too hard without redesigning the supporting systems can backfire. Do small upgrades sometimes cause bigger problems than radical redesigns? They can. The SD50 shows how increasing power without re-engineering the entire system can trigger a chain reaction of reliability problems. It's the quiet kind of failure, no explosions, no derailments, just mounting costs, frustrated operators, and fleets that never live up to their promise. What made the SD50 especially painful was that nothing failed in a serious way. Instead, shops were constantly busy chasing small issues. Components wore faster than expected, electronics failed, downtime went higher and higher, and the crews lost confidence because the engines were unpredictable, not because they were unsafe, but because they were always almost right. That kind of incremental mistake stands in contrast to designs that were radical from day one. Number 3. Fairbanks-Morse BL2. Moving on, we have Fairbanks-Morse experiments, great engines, poor locomotive outcomes. Fairbanks-Morse built brilliant opposed piston diesel engines, famous in submarines and ships, but translating that success to railroads was messy. The engines were powerful and compact, yet complex to maintain in everyday rail service. Their locomotives showed promise, but parts availability, cooling challenges, and maintenance demands made them less attractive than simpler, standardized competitors. Great technology, wrong ecosystem. Military-grade ideas don't always belong on commuter rails, and that truth became painfully clear with Britain's next experiment. And here's the part that makes engineers uncomfortable. Some locomotives didn't fail because they were bad ideas. They failed even after the engineering worked. In fact, the final entry on this list proves that sometimes being right isn't enough to survive. Number 2. British Rail APT. British Rail APT, the tilting miracle that politics killed. The advanced passenger train was revolutionary. It could tilt into curves, allowing much higher speeds on existing tracks. In testing, it set records and proved the physics worked. But early passenger runs exposed teething problems, uncomfortable ride sensations, and reliability hiccups. The press turned hostile, political patience evaporated, and the project was shelved before it could mature. Years later, tilting trains returned, but the APT never recovered its reputation. Could the best engineering on paper fail because of bad PR and politics? Yes. The APT's technology was sound, but early issues, media backlash, and a lack of long-term support doomed it before the engineering could be refined. But railways don't operate in laboratories. They operate in public view. Passengers weren't ready for how tilting actually felt. It was new, it felt strange, and for some people it was uncomfortable. The press pointed out on every small issue, and those stories spread faster than engineers could fix anything. Once the headlines turned bad, political backing disappeared. Money dried up, and confidence went with it. It stands as one of the clearest examples that public trust is as critical as mechanical success. We've seen overreach, rushed upgrades, and misunderstood breakthroughs, but the final story is about a locomotive that worked and still lost. Number 1. Virginian ELC/E33. Meet Virginian ELC and the afterlife of electrification. These locomotives weren't mechanical disasters. They were advanced electrics, powerful, efficient, and perfectly suited to their original routes. But when railroads merged and priorities shifted, electrification was abandoned in favor of diesel. The infrastructure disappeared. The locomotives became orphans, sold off, reclassified, or scrapped, not because they failed, but because the world around them changed. What's worse than a locomotive that fails technically? A locomotive that works fine, but loses the system that supports it. The ELC machines weren't beaten by engineering, they were beaten by economics and policy. When you step back, patterns emerge. Some engines were too big for the rails they had to run on. Some relied on exotic technology that never got the time or maintenance culture it needed. Others had the wrong mission for their design. And some were simply victims of politics, mergers, and shifting priorities. So what matters more, a brilliant idea or a brilliant rollout? Both. Engineering doesn't live only on the drawing board. It lives in workshops, budgets, schedules, and public perception. Most failed locomotives didn't fail in isolation. They failed at the intersection of technology and context. We don't tell these stories to mock the past. Every machine here pushed boundaries, new boilers, new wheel arrangements, electrics, tilting bodies, radical engines. They were laboratories in metal. Sometimes the lab exploded. Sometimes it taught the next generation everything it needed to know. Modern traction still carries those lessons. Should engineers stop being bold to avoid failure? No. But boldness needs humility. Fail early, learn fast, and build systems that can survive beyond the prototype. These locomotives may be remembered as failures, but they're also the stepping stones that made today's railways possible. If you love mechanical misadventures and engineering near misses, hit like and subscribe. If you enjoyed this video, please make sure to check out our previous video, and don't forget to drop a comment. Which machine shocked you the most? And which one should I deep dive next? I'll see you in the next one.